Hello friends, subscribers and new viewers of this channel. In this tutorial we explain rotation matrices in robotics. There are at least two approaches for deriving rotation matrices. In this tutorial we will explain the first approach, and in the follow-up tutorial we will explain the second approach. Both approaches will arrive at the same result. I will provide a link to the follow-up tutorial in the description below this video. First, let's start with the problem formulation. We consider a body that's rotating around a fixed point. And here is a 2D representation of the cross-section of the body. Here's our body, or better to say its cross-section, and this body is rotating around this point O. And it rotates like this. We are observing this scene from the tip of the z-axis, and this is just a cross section. Then, to this body, we can attach a body frame or a body coordinate system that's fixed, and here it is. This is the horizontal axis, and this is the vertical axis. This is x, b, and this is yb. Now, after some time, the body will rotate and it will go to this position. Since this coordinate system, that's called the body coordinate system, is fixed to the body, it's going to rotate together with the body. And at certain time instant, the axes are going to be oriented like this. This is going to be xb, and this is going to be yb. In our initial position, we can consider a vector rb. Here it is. And this vector is written like this, r with the left superscript b. As the body rotates, this vector will rotate with the body. And consequently, at this time instant, that is, after the body rotates for a certain angle, the vector will be oriented like this. Here it is, RB. Now, since this vector is a body vector, it's continuously rotating. However, this angle over here that this vector makes with the xb axis is always constant. That is, over here is alpha, and over here it's also alpha. From outside, it looks that this vector rb is continuously rotating. However, if we imagine that we are just sitting in this coordinate system xb, yb, this vector will always stay constant. That is, it's not going to rotate if you are located in the coordinate system xb and yb. Over here, to make the previous two graphs less busy and to make this tutorial to be more clear, I raised the body. And let's again sketch the vector rb. Here it is. And over here is the vector rb. Again, a very important thing to keep in mind that this angle over here, alpha, is always constant. That is, alpha doesn't change as the coordinate system b rotates. The vector rb has projections in the coordinate system b, and these projections can be constructed like this. Here's the projection onto the axis xb, and this projection is the distance from here to here. And this projection is denoted by rb xb. The vertical projection is constructed like this, where this angle here is 90 degrees as well as this angle over here, and the projection is the distance from here to the coordinate 0. and the projection is denoted by RB, YB. Okay, similarly over here we can construct the projections. Here is the horizontal projection. We just draw a normal to the axis XB, and the projection is the distance from 0 to this point, and again this projection is denoted by RB, XB. Similarly, the vertical projection is constructed by drawing a normal to the axis YB, and here it is. It's a distance from this point to 0, and it's denoted by RYB, and don't forget here the left superscript B. Here are the two projections. From the mathematical point of view, the vector RB with its projections can be written like this. R with the left superscript B is equal to, then we open these vector brackets and we write, first of all, the horizontal projection, it is R, XB, don't forget B over here, and RB, YB. And then you need to close these vector brackets. Over here, for clarity, I repeated the last figure and I eliminated redundant notation and redundant symbols. Okay, let us assume that at certain time instant, for example t, the coordinate system B rotated for the angle of theta with respect to some horizontal axis. And let's denote this horizontal axis over here as XA. And let's construct a Cartesian coordinate system by using this horizontal axis. That is, let's just add over here a vertical axis. Here it is. This is YB, YA actually. Now we have two coordinate systems. We have the coordinate system A, and we have the coordinate system B, and the coordinate system B is rotated for the angle of theta with respect to the coordinate system A. And here is the angle of rotation theta. Okay. Now, it is important to observe the following. The vector RB also has the projections in the coordinate system A, and here are the projections. This distance over here is the projection of the vector RB onto the axis XA. And let's denote this projection like this. RB XA. That is the distance from here to where this normal intersects the XA axis is RB XA. Similarly, we can construct the projection of the vector RB onto the axis YA. And here's the projection. We just draw a normal over here. And here's the projection. I'm not going to make this graph busy by drawing a line from here to here. However, you know that the projection is the distance from here to here, and this projection is denoted by RB YA. Here's the problem formulation. Given the vector RB with its projections in the coordinate system B, that is given RBXB and RBYB, and given the angle of rotation theta, we want to determine the projections of the vector RB in the coordinate system A. That is, we want to determine RB XA and RB YA. Okay, let's reformulate this problem graphically. So what we are given? We are given this projection, that is the projection of the vector RB in the coordinate system B, and we are given this angle theta, and we want to determine this projection and this projection. That is, we want to determine the projections of the vector RB in the coordinate system A. In this tutorial, you will learn that this problem has a very elegant solution. Namely, the solution will look like this. We will be able to express the vector RB in the coordinate system A like this. Let's write it here. RB in the coordinate system A will be equal to a matrix R denoted like this. Left subscript is B and the left superscript is A, multiplying the vector RB. This matrix over here is called the rotation matrix. So what does this matrix do? It takes the vector in the coordinate system B and transforms its projections into the coordinate system A. And the transformation is performed by simply multiplying a vector by a matrix. And this matrix is called the rotation matrix. This rotation matrix will depend on sines and cosines of this angle theta. Furthermore, this notation over here, BA, means that we are actually transforming the coordinate system B into the coordinate system A. Okay, let's start with derivations. First of all, let's simplify the notation a bit. Let's denote the intensity of the vector RB like this, simply as RB. And let's continue. First of all, let's see what is this projection RBXA. We can write this projection like this. RBXA is equal to the intensity of the vector RB multiplied by the cosine of alpha plus theta. So let's write it like this. It's simply the intensity of the vector B multiply the cosine of this angle, alpha plus theta. Good. Similarly, we can write this projection RBYA like this. It's equal to the intensity of the vector RB multiplying sine of alpha plus theta. Good. On the other hand, from the basic trigonometry, we have the following relations. First of all, this term cosine alpha plus theta can be written like this. Cosine alpha plus theta is actually equal to cosine alpha multiplying cosine theta. Then we have minus sine alpha multiplying sine theta. Then we have that sine alpha plus theta, that is this term over here, can be written like this. Sine alpha multiplying cosine theta plus cosine alpha multiplying sine theta. And let's use these two formulas and let's substitute them in these two equations. Let's start with the first equation. We can write RB XA is equal to RB multiplying this term minus RB multiplying this term. So let's write these two terms over here. We will have RB, that is the intensity, multiplying cosine alpha, cosine theta, minus RB multiplying sine alpha, sine theta. Good. Then let's write the second equation. The second equation reads like this. RBYA is equal to, again, RB multiplying the first term plus RB multiplying the second term. So we have RB over here multiplying, let's see what we have, sine alpha cosine theta plus RB over here cosine alpha sine theta. Good. Here for clarity, I wrote again these two equations. Let's analyze these two equations. And let's consider this graph. So what is RB multiplying cosine alpha? Let's look at this graph. Okay, so RB is actually the intensity of this vector, and here is the angle alpha. And if we multiply RB by cosine alpha, we actually get this projection, RB xb. Good, so let's write it down. We will have Rxa b is equal to, instead of RB cosine alpha, we will simply write the projection RB xb. And over here we will have cosine theta. Good. Then we will have a minus sign. Again, RB is the intensity of this vector. If we multiply the intensity by sine alpha, we will actually get this projection. That is, we will get RBYB. Consequently, instead of RB sine alpha, we will simply write the projection RBYB. And here we will have sine theta. Let's apply the same principle to the second equation, and consequently we will have RYAB will be equal to RB sine alpha is actually this projection, so let's write it down, RB YB, and we will have over here cosine theta. Then we will have plus sign, and RB cosine alpha is actually this projection, plus RB xb, multiplying over here we will have sine theta. Good. And we are almost done. Next, let's write these two equations in the vector form. So let's write it down. Let's start from here since we will need some space. Over here, I will have R, X, A, B, RB, YA, and let's see what do we have over here. Then I will have a matrix over here, and for the time being, I will just write an empty matrix. And over here, I will write the projections of the vector RB in the coordinate system B. Consequently, I will have over here RB, XB, and over here I will have RB, and then I will have YB. And then I will close this vector. Let's see what do we have inside. Let's analyze. We have over here RBXB, and this term is multiplied by cosine theta. Consequently, over here we will write cosine theta. What do we have over here? We have RBYB, and this is multiplied by minus sine theta. Consequently, minus sine theta. Good. This is the first row. How about the second row? Let's see what do we have over here. We have over here RBXB, that is this term over here, multiplied by sine theta. Consequently, over here we need to put sine theta. And what do we have over here? We have RBYB, that is this term, multiplied by cosine theta. So here it is. And we arrived at our solution. This vector over here can be written like this. This is actually the projection of the vector RB in the coordinate system A. And over here, this term is actually the vector RB, and consequently, this equation can be written as, let's write it down here. We will have RB as a vector, or let me just improve this notation, RB as a vector in the coordinate system A is equal to the rotation matrix. That is, this matrix over here is the rotation matrix, and it's denoted like this. Rotation matrix of B with respect to A. That is, this rotation matrix will rotate the coordinate system B into the coordinate system A. And that's why we have this notation multiplying over here RB. That is the vector RB in the coordinate system B. And this is the final result. Again, this matrix over here is the rotation matrix. Here is a brief summary of what we learned in this video tutorial. To transform the vector RB from the coordinate system B to the coordinate system A, we need to take the projections of the vector RB in the coordinate system B and we need to multiply them by the rotation matrix. This rotation matrix depends only on the angle theta, that is the angle of rotation between the coordinate system A and B, and as the result we are going to obtain the projections of the vector RB in the coordinate system A. This equation can be compactly written like this: RB as a vector multiplied by the rotation matrix from B to A produces RB in the coordinate system A, where this matrix RB with respect to A is the rotation matrix. Okay, that's all for today, and I hope that you like this tutorial and see you in the next tutorial.